You feel powerful. Okay, so chessboard cell color is our next one. And then if we pass that, we'll move on to 30, but I think we got to unlock it first. So let's take a look at what this one is asking us. All right, so there's nothing here now. That's good. And basically the idea is that this is a chess problem. I mean, no surprises there. It's chessboard cell color. So what we want to do is we're given two cells on a standard chessboard, which means it's an 8x8 grid, 8x8 matrix. And we want to say, do they have the same color or not? Okay, so basically, first thing to notice, the way we're going to be given these cells, it's kind of weird. Like we're given these almost like code names, right? So they say A1 to mean this right here. So there's the A, there's the 1, so that's A1. Whereas C3, it's this one right here. Okay, so that's sort of the code they're going to use, but maybe we do want to treat this more like a matrix, in which case A1 and C3 are not going to be that helpful. So let's write a function called getCoordinates, and it's going to take in, I guess, a position, I guess we'll call it. And the idea is that position has two parts. It's got the alphabetical part and the numerical part. So we'll start with the alphabetical part. So we'll say let x be assigned the value of position dot character code at 0. So we're getting the character code of the first letter, and we're going to subtract from that the character code of the letter capital A. Okay. So the reason we're doing that is because it looks like we're getting capital letters as inputs here. And we're basically just going to say, well, if it's A, well, that's 0. If it's B, that's 1. If it's C, that's 2, etc. And then for Y, we're going to set let Y be assigned the value of position at 1, except we want it as an integer. So we're going to do a parse int on all that. And there are other ways of doing this, you know, like you could just multiply it by 1 or something like that, but it feels a little wrong to me. I don't want to do it like that. So we're going to say return x and y. Great. Okay, so that's going to give us the coordinates at a given position. Let's see if it's working. So we'll say return get coords of cell 1. And we should get, I guess, like 0, 0 if cell 1 is A1. 0, 1. Ooh, yes. Okay, so I forgot. We want to subtract 1 off of this one because right now these are 1 based. We want them to be 0 based. I mean, essentially what we're looking for is something more like this, like 0, 1, 2, 3, and then over here 0, 1, 2, 3. Okay, etc. Right? So there we go. We're getting our 0, 0 just as we suspected here. And then I think like almost all of these have A1 as the first one. There's B3, so great, 1, 2. B3, yeah, 1, 2, that looks good to me. Okay, so this is giving us our coordinates. And, you know, just while we're here, maybe we also want to get one that's get position, and we're given coordinates, or we're given, we'll say an X, Y, we're given that coordinate separately. So from that, I guess we would do something like, return string dot from character code, and we want the character code of capital A once again. So maybe I should do a constant for that like I was doing before, but we'll see. Plus x, and then we want to concatenate that with y plus 1 dot to string. There we go. Okay, so now I guess let's just test that one. Let's say get position of 3, 5, let's say. Okay, so 3, 5, 3, 5, it should be, I guess, D6. Yeah, great. All right, so those two are working. We can sort of convert between these two types of data, which is nice. I mean, that's something that's fairly common, that, you know, if we're looking at a problem where we're given data in one form, but really we'd be more comfortable with the data in a different form, like coordinates, then it's pretty common that we'll sort of have these functions just for like converting. There are other ways we could do it, you know, like we could use an object or something like that and have a constructor for that object that takes in one of these. Like that would work too, and who knows, maybe it's a better way of doing it. But for now, we're gonna look for some patterns here. So first thing I want to point out is basically if we're on the chessboard, and just for the sake of this example, I kind of want to flip these around. So I'm just going to say we're starting at this cell right here. We're going to start at C3, and we're going to try to make our way to A1. Okay, so the idea here is basically that if we're on this cell right here, then we have like 4 places we can move if we're just going up, down, left, or right. And the other thing I want to say is if you are moving on the chessboard in such a way that you're only moving up, down, left, or right, then every move you make, no matter which direction it's in, you will change cell colors. The chessboard you'll be on a different color every time. So on a dark square, move to a light square. Move in any direction, you're on a dark square again. Back on a light square, dark square, light square, dark square. So basically every move we make, and keep in mind it can't include diagonals, but every move we make is going to alternate the color of the square. That's the idea. Okay, so we're going to start with this right here. That's our first cell, and we're going to radiate outward from there is the idea. So we're going to say, all right, so if this is our first square, what other squares are accessible from that one? So that one, that one, that one, and that one. All right, great. So then that's all of them, right? So from there, we'd say, well, what about these guys? What squares can we access from these? So we'll say, well, we could access that one, that one, and that one, and that one. And this is maybe starting to look a bit like a previous challenge we did called shape area. Anyway, maybe there'll be a connection there, maybe not. The point is, we've identified all the squares that are reachable from these ones. So then we'll say, okay, what about this round of squares? Which ones are reachable from there? If we're just going up, down, left, and right, we can access all the ones on the outside here. And you notice that some of these are starting to go like off the chessboard, so we're not going to count those. All right, and then finally, on our next iteration, what we're going to notice is that as we're radiating outward, like for this next round, one of the cells we're going to hit, it's going to be A1. So at that point, we could stop and we could say, all right, how many steps did we take? Because the point is we don't know where one is with respect to the other, or at least we're going to say right now that we don't. The point is we're starting with a very naive interpretation. We'll maybe look at other ways after, but for now, we're starting here, and every move we make is going to change the color. So we're going to change the color 1 time, 2 times, 3 times, 4 times by the time we arrive at A1. Okay, so this is going to be our first implementation. It's going to be our first interpretation of the problem. We're going to start at cell 1. And then we're going to look at all the possible cells that we can move to. So we would say kind of like, in terms of the number of moves here for each of these cells, we're starting with 0 moves over here. And then for each of these, it's going to take 1 move to get there. And then for each of these, it's going to take 2 moves to get there, et cetera, et cetera. I'm kind of representing that through color, I guess, right now. But the main thing is that as we continue outwards, so we've got 0, 1, 2, 3, 4. So we get to here, 4. And the last thing we're going to check is we're going to say, well, this number of moves that it took to get to that final cell, is it even? Because if it's even, then that's pretty much all we need to know, right? Because like we said before, every time we change cells, every time we make a move, it changes the color. So if we were to change the color an odd number of times, then we're talking about different colored cells. If we were to change it an even number of times, well, we're back to the original. So that's what we're going to check. Okay, so that's our plan from here. We're going to start at cell 1. We're going to explore all the possible cells that we can move to from there. Once we've gone through all of those, we're going to look at the next round of cells that we can reach from each of those. And we're going to continue that process until we get to cell 2. And while we're doing this, the other thing is that we're going to be keeping track of how many moves it took to get there. Okay, so like I said, we're going to start with our most naive interpretation, which means we're actually going to be making a matrix here. Field, no, I'll call it board, I guess. because it is a chessboard after all. So board is going to be assigned the value of just this empty array, and we're going to say for let I be assigned the value 0, I is less than 8, and I plus plus. And then within there, we're going to say let row be assigned the value of an empty array for let j be assigned the value 0. J is also less than 8, j plus plus. We're going to say row dot push, and we'll just make it a 0 for now, I guess. And then we'll say board dot push row. Okay, so our board should basically be a whole bunch of zeros, 64 of them specifically. So 8 rows of 8 zeros, and that's what it's looking like. Okay, great. That's what we want. Okay, now the way we're actually going to be traversing this, the way we're actually going to be able to get from here to here, if you think about it, it's kind of like we're using a search algorithm, and specifically we'd be talking about something kind of like a breadth first search. Now, the reason I say a breadth first search as opposed to a depth first search is a depth first search would probably do like, oh, we'll try this, and then eventually get there, that sort of thing. But that's really not what we want. That would give us a false impression of how many moves it took to get there, because we're sort of looking for, well, I was going to say we're looking for a shortest path, but I guess it doesn't really matter. Like as long as you find the cell, then, like, no matter what path we take to get from here to here, it could be very roundabout, but as long as we're not taking any diagonals, then if we get there in an even number of steps, then that's good. That means we have the same colored square on both of those cells. Okay, so if you've never done a search algorithm before, this might be a little bit intense. I do definitely recommend reading about breadth first search, depth first search. Those are both really useful algorithms, and you'll find you'll probably use those a lot. So the way we're going to do this is we're going to basically have, I guess, 3 things that we're keeping track of. So first of all, we're going to say visited. These are going to be the cells that we've already gone to, that we've already seen. Okay, so visited is going to start as an empty array. And then we're going to say let Q, which is kind of a funny word, UE. Anyway, Q is going to be just cell 1. Okay, so we're going to start with cell 1. That's going to be in the queue to begin with. And then the queue is basically going to be like the list of all the squares that are reachable that we're going to use for the next one, right? And basically the idea is that while the queue is non-empty, we're going to be, well, first of all, we're going to take something out of it. So we're going to say this is q.pop. So that's our position. It's like our next element. We're then going to say visited.push that position because we have visited it. And then from there, we're going to say, I guess we'll do something like this. So we're going to assign 2 variables here. We're going to say x and y are going to be the result of get coordinates on position. Okay, so like there are other ways we could assign this. We could say something like chords. Wow, that is a very loud truck. Okay, sorry about that. So we could do something like this, like chords be get chords of position, and then x would be like chords at 0. We could say let y be chords at 1. And that would give us like all of this over here. That would be the same as this. It would work the same way. This is just a more efficient way of doing it. We get x and y together this way. Okay, great. So we've got our x and our y, and we might as well say, okay, well, before we go any further, let's search for next ones, right? So we'll say for let dx be assigned the value of -1, dx is less than or equal to 1, dx plus plus, and for let dy be assigned the value of -1, dy is less than or equal to 1, dy plus plus. Okay, so then basically the idea is we're looking kind of in all directions, right? Like we've got a dx, which is -1, 0, or 1. We've got a dy, which is -1, 0, or 1. And so we want to look in all directions, but we actually don't want to look in all directions. Like we don't want dx and dy to both be -1 because then we'd be looking at this. We just want the ones that go up, right, down, and left. Those are the ones we're interested in. Okay, great. So basically we'll say if math.absolute of x plus math.absolute of, sorry, not x, dx is what I meant, and dy. If the sum of the absolute values of these two is 1, well, my claim is basically that means we're going up, down, left, or right, because the only way this could be true, that this is 1, is if exactly one of these things is either 1 or -1 and the other one is 0, right? So if dx is -1 and dy is 0, let's say, then the absolute value of their sums would be 1. Let's say if dx was -1 and dy was +1, well, that would mean that their absolute values would actually sum to 2. So there are other ways you could do this, but basically I'm using this if to just get up, down, left, and right. Okay, so that's the idea behind this line right here. All right, so let's use this now. Let's say let temp x be assigned the value of x plus dx, and let's let temp y be assigned the value of y plus dy. And then we'll say let temp pos be get position of temp x and temp y. So it's nice that we sort of wrote these functions to begin with up here that sort of get our coordinates or get our position. So we're going to use those down here. Okay. And then basically what we want to say is, well, is it off the board? So we want to say, is temp x between 0 and 8? And also we want to say, is temp y within that same range? And temp y is less than 8. Okay. And there's one more thing we want to say as well. We want to say, well, visited dot index of, what is this, temp pos, yeah, temporary position, equals -1. In other words, if it's not yet visited, if we're talking about a new position which we haven't visited yet, well, in that case, we're going to say, well, we're going to start this next queue. Okay, so we're going to say let next queue be an empty array to begin with. And for this, we'll say next queue dot push, or I guess since it's a queue, I'll do an unshift, but it's not really going to matter here for reasons we'll see. And I should spell that right. There we go. So under those circumstances, we're pushing it into our array that we're going to look at next. Okay, great. So then that's going to look at all the neighbors up, down, left, and right. And basically that ends here. Okay, so once we reach the end, we've got all our new neighbors. Basically what we're going to do there is we're going to say, okay, so this is actually, well, it's not so much there that we want to do stuff, because I'm actually more interested in when the queue is empty, what are we going to do? So once the queue is empty, or actually, I'm missing a line here. Well, okay. So I actually need another loop here. And I guess I'll show you why in a sec. Maybe I'll just do it this way. Board at x at y is assigned the value of 1, let's just say. So we'll run that and we'll see if that works. So that doesn't really do anything. It's just putting a 1 in our A1, because keep in mind our queue doesn't really have anything in it to begin with. So it might seem weird that I'm putting this into the next queue instead of just the regular queue. There's a reason for that. I mean, basically, if we were to run this, what we would find is, I think this should complete, but maybe it'll enter an infinite loop. Oh, it did, but only on test 3. So yeah, that one worked. Basically, it found all the cells, eventually gave them all a 1. Why did this one not work? Execution time limit exceeded. So that one timed out. I wonder why. So we're saying while queue.length. Yeah, I guess it found that it was trapped and that it couldn't progress from there. So In some ways that's a little troubling, actually. I wonder why it would do that. I would have expected this to actually get to the ends here, but oh well. Let's. I guess we'll keep going from here. That is surprising though. I would think that the queue would empty. Maybe let's get a little console log and see what's going on with the queue there. Is this a good place for it? I'm not sure. We'll find out, I guess. So yeah, output limit exceeded. So that's not saying that it stopped. It's just saying, oh, there was way too much stuff in here for me to possibly be able to show you all this. Okay. Yeah, and we are pushing to visited. So, all right. I'm not really sure then why that third one isn't working. I feel like it should be stopping. Let's see. Yeah. Yeah, because it's only filling up the queue if it finds something that hasn't already been visited. Ooh. Okay, I have an idea. I think it's where visited is happening. So let's say visited.push, and we'll do temporary position over here. And then visited to begin with will just be cell1. Yeah, let's try that. Okay, great. So that actually did complete. That's better. That's what we're looking for. And it's all ones everywhere. The thing is, we don't really want it to be ones. We want it to represent how many moves we need to make. So we're going to say for let moves be assigned the value of 0. We're going to say visited.index of cell 2 is -1. So while that's still true, you know, as long as it hasn't found cell 2 yet, then we're just going to keep this loop going. And every time it does go, it's going to increase moves. Okay, so I'm going to cut that out. And what are we using moves for? Well, basically the idea is that instead of this being 1, we're going to make this moves. Okay, so then there's one thing we need to do at the end of this loop, because right now we're just pushing to the queue, right? Or unshifting to the queue. So at the end of this loop, basically, what was it called? Next queue? Next queue. Okay, great. So we're filling up the next queue, and eventually once we run out of elements in the actual queue, then we want to say, oh, okay, well then queue is going to be assigned the value of a deep copy of next queue, and then next queue is going to be empty. Just empty it out. Okay, and then at the end we want to return our board. So let's see if that's going to work. This is one of the more complicated algorithms we've written. Well, I guess I should put the third dot in there, eh? So keep that in mind. With a spread operator, we do need all three of these. It's got to be a full-on ellipsis. Okay, great. So yeah, that is kind of a complicated algorithm. Is it working? Ooh, it's working. So notice how we started at A1, and then we can see sort of what we were looking at before. We've got 1, 1, 2, 2, 2, all the 3s over here. But then it stopped at the 3s. Why would that be? Well, because it found C3. That's what we were looking for. If we look at this next one, it was looking for H3, so it had to go further. It had to go all the way to 8 there. Test 3, that didn't really do much. I think it's because it found A2 right away, because they were neighbors, right? Okay, and then let's see. Okay, there's just one issue here now, I think. B2. Yeah, my worry here is that it should fire, I think, one more time after this, right? Because we're still getting, like, B2 in this case still has a 0. I actually do want to see, like, the 2, 2, and 2 here. So I want it to fire one more time than it's going right now. I think the issue might have to do with the visited being down here. Let me just switch this back to the way we had it before. So we'll say, I think it was here, right? Visited push position, and then visited starts as empty. Would it work if we did that, or would we encounter the issue that we saw earlier? I guess we'll find out in a sec. No, that's working. Okay, good. And it's actually working better because it's giving us yeah, the actual number we're looking for. So, like, you know, if that's A1, there's A2, and we actually do see a 1 there. Okay, so I don't want to return board. I want to do a console.log of board just so we can see what it looks like. And then what I want to return is basically, did it take an even number of moves? That's what I'm wondering. So what I want to return is board. Actually, hold on a sec. Let x2, y2 be assigned the value of get coordinates of cell 2. And what we want to return is if board at x2, y2, mod 2 is 0. That's basically saying, was this even? The number of moves that it took to get to cell 2, was that even? Was it an even number of moves? Because if it is, that means they have the same color. If it was an odd number of moves, they would have had a different color. And there we go. So that passes all the tests, which is nice. Like I said, it is kind of a complicated algorithm, so I'll go ahead and submit that just so that you can see my solution. You can click on that, take a look. Oh, and there we go. Okay, so I actually wasn't sure if that one was going to pass all the tests, but I guess it did. All right, congrats everyone. That's kind of like our first. Oh, nice, level complete. Gotta love that. 5,000 coin. Very excellent incentive. Okay, so this was a little complicated, wasn't it? I mean, you might think this is even, you might think this is kind of overkill. And yeah, I think maybe it is. Maybe this is overkill for what we're trying to do. So let's take all of this. I'm going to copy it because I want to archive it, right? So I'm going to comment out all this stuff for now, /*. Okay, great. And now we're going to start over. Okay, and we're going to try to simplify this a little bit because there are probably a few ways we could simplify it. So the first thing we could say is, well, look, we're doing mod 2 on this thing, right? Like at the end of this, at the end of all of this, we just went and did a mod 2. So we might think like, well, do we even need to put moves down? You know, like, do we even need to say that it's going to be moves? Like, couldn't we just say moves mod 2 and then just not have to do the mod 2 at the end? Just say, make sure it's 0 or something like that. And let's see if that works. Let's see if that gives us our actual board. Like, we should kind of expect it to be a little checkerboardy, right, with the 0s and 1s. So good. Yeah, that's sort of what we're looking for. 0, 1, 0, 1. And that answers the question just as well. I mean, we're passing all the tests. The thing is, I feel like what we've done here is kind of overkill if all we're looking for is those 0s and 1s. So I'm going to get rid of all of that, okay? All this was our search algorithm. We're going to get rid of that. That was a nice little intro to search algorithms. We'll look at those more in the future. But for now, yeah, it's too much for this problem. We don't need the full power of a search algorithm for something like this. So we've got our board here, and what I want to do now is basically just paint the board with 0s and 1s to begin with. So basically, we'll say over here, I guess, let square be assigned the value of 1. And then for each of these, every time, well, here, we'll do it like this. Let's say push square, get the square inside the array, and then square is going to be assigned the value of 1 minus square. So in other words, if square was 1 to begin with, then we're going to do 1 minus 1, which is going to be 0. If it was 0 to begin with, we'll do 1 minus 0, which is 1. So this is a way of alternating between 0 and 1. So let's run that, and we'll see. Well, actually, this stuff isn't, I don't think this stuff is going to work here, but the console.log should be fine. Okay, so that's not quite what we're looking for, right? I mean, each row looks good, but it should be alternating. Instead of 1, 0, 1, 0, it should be 0, 1, 0, 1. So let's do this. We'll say let start be assigned the value of 0, I guess. And then for every time that we do a new row, we'll alternate start. So we'll say start is 1 minus start. So the exact same trick we're doing down here, just to alternate between 0 and 1. Maybe let's just get a bit of space in here. It feels a little cramped, don't you think? Okay, so that's going to console log our board. And now I think it should look good. I think it's what we're looking for. Oh, no, it isn't. Okay, so why is that? Well, it's because we're saying square is 1. We're still saying that it's starting at 1. What we should be saying is square is start. Okay, let's try running that one. And with our console log, now it's looking good. Okay, great. This makes the problem so much easier. Because check this out. Now instead of saying, did it take an even number of moves? All we have to say is, are they on the same kind of tile? And we will use x1, we'll use x2, y2. We'll also use x1, y1. And hey, I just had a brainstorm. I am wondering something, which we're going to check in just a sec. But before we do, if you think about this, all we need to check is, are they on the same kind of tile? So, you know, if the first one is on a 1, is the second one also on a 1? If the first one is on a 0, is the second one also on a 0? So let's try running this, and we're still getting our board console logged because, you know, it's nice to see. And look at that, it's working. It's giving us the same exact answer, except we didn't need to worry about any of that like search algorithm business, right? So again, that was overkill. And since we're only using get coords here, we actually don't even need get position anymore. We don't need to convert it back to a position. So now our algorithm is getting a lot tighter. It's getting a lot nicer. It doesn't have to think as much. There's a lot less redundancy happening here. So that's good. All right, so it's passing all the tests here. Now, what I was wondering is this, because I figured like, we're doing kind of a similar thing with both of these, right? So we were able to declare x1 and y1 as like elements in an array, right? And then we're declaring this other like array here. I'm wondering if there's a way we could like even put these together, you know, like let x1, y1, comma, x2, y2 be assigned the value of cell1, cell2 dot map get coords, you know, something like that. Like, would that work? I don't know. That feels a little greedy. And even if it did work, it feels like, is that wise? Wow, that actually worked. Just pass all the tests? Guys, I didn't think this would work. Wow, okay, so cool. That's good to know. All right, we'll do that, I guess. I didn't think it would work that way. Is that clear though? Like, does that make sense for everyone? I like the way it looks so nice and compact. That's kind of cool. I mean, this is an area where I always tend to find this to be a bit of a pain. The idea that like, when we need to take an array of length 2 and use that as the coordinates for a matrix, you know, because like this isn't an array, like the x1 and y1, these are not in an array together. Well, you know, they are up here, but anyway, the point is like this is an x1 comma y1, it's x1 and then y1. So I've always found this to be kind of an awkward situation, and I really like this. This is, yeah, that's kind of cool. Anyway, all right, that was another way of doing it. We're basically just checking, are they on the same kind of tile? You know, we're just directly checking that. Okay, so that was another way we could do it. That was an interesting way, and it saved us, well, a lot of characters. You know, we basically were able to cut out all of this stuff and substitute it with just a bit of extra stuff in here. So that's nice. Yeah, that's a lot better, I would say. Okay, can it get better than that? Well, yeah, it can. And I mean, what it comes down to is basically, again, if we're moving up, down, left, and right, if we're not taking any diagonals, then we're really just looking to say how many steps did it take to get from cell 1 to cell 2, and in particular, was it an even number of steps? So if we take a look at it this way, we could say, well, let's just get the horizontal distance, and then let's get the vertical distance, add those together, and see if we get an even number. Let's try that. So now we're not actually going to use a board at all. We're going to get rid of this whole idea of board, and maybe actually I'll delete from here because we might use this down here. So here's what we want to do. We want to get the horizontal distance. Oops. We want to get the vertical distance. We want to add those to get the total distance. And then finally, we want to check, is it even? That's basically it. Okay, so we're going to start with this up here. This is our nice, beautifully efficient way to get the coordinates of each of our cells. And so the horizontal distance, let horizontal, or should I call it like h distance or something? Maybe that's nice. H distance is assigned the value of math.abs x2 minus x1. Okay, why am I doing the math.abs? Well, we don't know which one's bigger, right? It might be x2, it might be x1. If x1 was bigger, then x2 minus x1 would give us a negative, which is not what we want. We want to get positive numbers here. But now that I think about it, mathematically, it might not actually matter. Huh. I wonder. Yeah, because like if you subtract two even numbers, you get an even number. If you subtract an even and an odd, you get an odd. So yeah, we probably don't even need the math.abs here, but we'll see. We'll see eventually. Let total distance. Yeah, it's a bit inconsistent, but oh well. H distance plus vertical distance. There we go. Is it even? So all we really need to return is total distance mod 2 is 0. That's pretty much it. So let's try running that. We got the horizontal distance, got the vertical distance. Boom. There we go. Okay, so that's pretty nice. It's getting a lot more efficient than it was before, which is nice. Okay. So, but there's one thing that we noticed, which is basically like if actually, here's one thing that we can notice here. Check it out. So I'm gonna choose a really excellent color, and we're gonna take a look at something down here. So basically, let's say that we do want to use these numerical coordinates, pretty much using these throughout. So it's nice that we wrote that that function at the beginning there. And now basically what I want to do is I want to take a look at the sum of the coordinates for each square here. So if we look at the first square, it will have a sum of 0. Okay? Whereas either of these here would have a sum of 1. Okay? Let's use x's for those ones. Which ones have a sum of 2? Well, it could be 0, 2. It could be 1, 1. Or it could be 2, 0. What about a sum of 3? Okay, well that could be 0, 3, 1, 2, 2, 1, or 3, 0. Okay, and then for the ones that add up to 4, we find it's these ones over here. Here's the thing. I mean, I'm basically using O's to represent even sums and X's to represent odd sums. But the thing is, notice every O is on a dark square. Every X is on a light square. So another way of saying this, another way of telling what type of square you're on is if the sum of your coordinates is even or odd. Okay. So basically we could do something like this. We could sum our coordinates. Well, basically what we're checking for is this. Okay. We want to say x1 plus x2, x1 plus y1, sorry, is the same as x2 plus y2. But that should be mod 2, right? So x1 plus y1 mod 2 is the same as x2 plus y2 mod 2. And we'll see if that works then. I mean, yeah, that's all we need to say. So, I mean, could it be simpler than this? Well, yeah, it probably could be. I mean, maybe we could do something like minus x2 minus y2 and just put these all together as 1 and see if that is going to be equal to 0. And there we have it. Okay, so is it going to get simpler than that? That might be asking for a lot. I feel like this is getting pretty darn simple, so maybe we'll leave it at that. Hopefully this passes all the hidden tests and all that. Okay, great. All right, so that was a bit of a longer one. That was kind of intense. So when we look back, you know, taking a look at our first algorithm here with the whole search happening, 2 other nested functions, like that was a lot compared to this especially. And like we could probably make this a little bit simpler. Like we don't necessarily need to make this a function, but I think it's best to do it like this. Okay, so hit up number 5124 if you want to take a look, a more detailed look at this solution here. I realize it was a bit of a bumpy ride at the start here, but we got through it. We were able to get a very simple algorithm at the end. So if you are interested, like in the search algorithm we use down here, feel free to check that out. Like I said, 5124. Anyway, we're probably going to move on from here. We'll go on to the next one.